The problem from Gate Physics 2012 reads as follows. In the following circuit, for the output voltage to be V0 equal to minus V1 plus V2 by 2, the ratio R1 over R2 is, and the four options are given as half, 1, 2 and 3. Now, before solving any op-amp related problems, we first ask ourselves a few questions. Like, first, is this op-amp ideal? Now, let's look at the question. The question is silent whether it's ideal or not. So if the question is silent, we'll assume that it's ideal. If it's non-ideal, the question must explicitly mention that. Second, is there any feedback? Now, we know we have seen the feedback and we define the feedback if the output node is connected to any of the input nodes. So we see that the output node here is in fact connected to the inverting terminal of the op-amp. So we see that yes, there is a feedback. And what kind of feedback? Negative feedback. Why negative feedback? Because the output node is connected to the negative terminal or the inverting terminal of the operational amplifier. Now, since this is an ideal amplifier, what we can say that the current flowing into the op-amp on the input side is 0. So both of these currents are 0. Right, and there's a very interesting property which we see in case of op-amps, and we're going to talk about it a bit. Right, remember that there was an R in here. So if I apply Ohm's law across this Rn, it would be V plus minus V minus equal to Rn times I. Since there's no current, Rn is usually a very high value like mega ohms. If there is no current flowing, then I can simply say V plus minus V minus equal to 0. This implies V plus equal to V minus. This condition is what we call as, virtual short. Why short? Because the potential of these two nodes is the same. Why virtual? Because they're not actually shorted. See, there's no wire joining these two. However, it's due to the peculiar property of op-amp that the inverting terminal has the same voltage as the non-inverting terminal, and we denote it by a dashed line. This dashed line denotes that this node and this node, which are the input terminals for this op-amp, are shorted, virtually shorted. Right. Now let's try to solve this problem. Now we were given the expression for V0 as this. I'll write it down here. V0 equal to minus V1 plus V2 by 2, and we are required to find the ratio of R1 over R2. Correct. Let me switch my pen. Okay, so as we talked about that there's a virtual short condition, so I'll do this, and let's assume that the voltage here is Vx. Naturally the voltage here will also be Vx. Now as no current is flowing in the op-amp, so this is what we say. Now let's assume a current I2 is flowing here. Now look at this node. So if I see KCL at non-inverting terminal, so what do we see? All the current that's flowing, the I2 current that is flowing, since no current is flowing in this arm, so all the current that I2 is coming from the V2, the voltage source, all of it has to flow through this resistor. Why? Because no current can flow through here. Similarly, let's assume a current I1 is flowing through here. So I apply KCL at this, and I got that I R1 equal to I R2, which I am simply saying as I2. Similarly, if I apply KCL at inverting terminal, again, so I'll current flowing through resistor R, this one. So since no current is flowing through this arm, so all, if I apply KCL at this node, so all the current that's coming through this direction has to flow here. So equal to IR, so okay, let's call this RF is equal to IRF is equal to, I'm denoting it as with notation I1. Okay, now what we'll do is let's apply let's write Ohm's law across this R1 resistor. Okay, because now what we will try to find is, we need to find an expression for V0, and in order to find an expression for V0, we'll write Ohm's law across different resistors. So let's first write Ohm's law across R1. So if I write across R1, I'll get V2 minus Vx equal to, the current flowing through this resistor is I2 times R1. Similarly, if I now apply Ohm's law across R2, I can write Vx minus 0. So across R2, the potential drop is Vx minus 0 equal to I2 times R2. Now from these two expressions, if I equate the value of I2, I can write that V2 minus Vx upon R1 equal to Vx upon R2. From this, I can get Vx as V2 R2 upon R1 plus R2. Let's call this expression 1. Now, let's create some space. Now we'll write Ohm's law across the resistor R. So I can simply write V1 minus Vx equal to, the current is I1 times R. Similarly, Ohm's law across RF, I can write Vx minus V0, that's the potential drop across the resistor RF, equal to current flowing is I1 times RF. So from these two expressions, I can get V1 minus Vx upon R equal to Vx minus V0 upon RF. So from this I can get Vx equal to, note that R equal to RF. So RF was R, so this gets cancelled. So Vx we get is, the value of V0 I can get is simply, the value of V0 will be minus V1 plus 2 times Vx. It's just a rearrangement of the terms. Now compare this value with the expression given. The expression given is V0 minus V1 plus V2 by 2. This clearly means that comparing these two expressions, I can get 2Vx equal to V2 by 2. This implies Vx equal to V2 by 4. But we already know the value of Vx from as this expression. So I'll put the value of 1 here. So I'll get V2 R2 upon R1 plus R2 is equal to V2 over 4. So everything gets, V2 and V2 gets cancelled. I get 4R2 equal to R1 plus R2. And this will give me as 3R2 equal to R1. This is the expression that we got. So we got 3R2 equal to R1. We were required to find R1 over R2. So we take this here, that's 3 over 1, that's 3. So the correct answer is D. Thank you for listening.